Geometric sequences, example 5. Find the number of terms in the geometric sequence 81, 27, 9, up as far as 1 over 27. And notice that there's a full stop at the end, so that's indicating that's the final term in this particular geometric sequence. So we're going to write out our sequence. We're going to label the first term as A. We need to work out or the common ratio. So we're going to divide the second term by the first term. So we're going to divide 27 by 81, and we end up getting a third. So the common ratio is a third. So from 81 to 27, we're multiplying by a third. To get from 27 to 9, we're multiplying by a third, and so on. So we're going to keep multiplying by a third until we get to 1 over 27, and we want to figure out how many terms there is in this sequence. So we're going to use this formula. It's from the formula book. No need to learn it off. So Tn is equal to A times R to the power of n minus 1. So that's in your formula book there under the geometric sequences or series section, where A is the first term and R is the common ratio. So Tn is our final term. So we're going to replace that with 1 over 27. So that was given to us in the question, highlighted in yellow. A is our first term. We replace that with 81 on a set of brackets. R is the common ratio. We replace that with a third in a set of brackets, and that's to the power of n minus 1. So now we're going to solve for n because that will give us the number of terms. So it didn't ask us to find n in the example, but that's what they're actually asking us to find. The number of terms means find n. Okay, so we're going to divide both sides by 81. So 1 over 27 divided by 81 gives us 1 over 2187. And then dividing the right-hand side by 81, we'll just cancel out that 81. So we can just get rid of it and bring down the third to the power of n minus 1. So 1 over 2187 gives us 1 over 3 to the power of 7. And this comes from logs. So we want to rewrite 2187 as a base of 3. So we can say 3 to the power of x is equal to 2187. So log base 3, 2187 will give us x. So using the scorpion tail method, it's a scorpion tail method in reverse. So 3 to the power of x equals 2187. So 3 to the power of x equals 2187. So x is equal to 7. So 2187 can be rewritten as 3 to the power of 7. And that's going to help us to figure out the rest of the question because we have a 3 on the right-hand side and we have powers. So that's going to help us. So this is going back to the indices chapter. So the rest of this question is pretty much indices and algebra. So the next thing we're going to do on the right-hand side is to rewrite 1 over 3 as 3 to the power of minus 1. So this is one of the rules of indices. So we don't need to learn off the formula. It's given to us in the formula book. So we need to rewrite 1 over 3, so a third, as 3 to the power of minus 1. So just like if you had a half, that could be rewritten as 2 to the power of minus 1. If you had a quarter, that could be rewritten as 4 to the power of minus 1, and so on. Okay, so likewise with 1 over 3 to the power of 7, we're going to rewrite that as 3 to the power of 7 raised to the power of minus 1. So that's using that indices rule as well. So 1 over 3 to the power of 7 is 3 to the power of 7 raised to the power of minus 1. And we're just going to bring over the 3 to the power of minus 1 raised to the power of n minus 1 on the right-hand side. So that's all I've done there, nothing new. So 3 to the power of 7 raised to the power of minus 1. The indices rule here is we multiply the powers. So 7 multiplied by minus 1 is minus 7. And then 3 to the power of minus 1 raised to the power of n minus 1. We can break this up into two parts. We have a numerator and a denominator because that minus there means divide. So this is another one of our indices rules in reverse. So the rule is dividing powers with the same base, we subtract the powers. So here we're starting off with the subtraction, so it becomes divide. Notice that the 1 is now positive. That's really important. It doesn't become -1. It's positive 1 because the minus represents the divide line. So in the next step, we're just raising powers to a higher power. So we're going to multiply the powers. So -1 multiplied by n is -n. And -1 multiplied by 1 is -1. So that's all that happened there. So that's another one of the indices rules. Raising a power to a higher power, we multiply the powers. And then again, we are dividing powers with the same base, so 3 being the base. So that rule again that we had up here, but we had it in reverse up here. Dividing powers with the same base, we subtract the powers. So we bring down the -n, the divide becomes minus, and then we bring down the -1. So we end up getting -n minus -1 as our power. And then -1 becomes +1. So our power is -n plus 1. Now we can cancel out the 3's because we have the same base on each side. So we can say -7 is equal to -n plus 1. So -7 is equal to -n plus 1. And now solving for n, we get n is equal to 1 plus 7. So n is equal to 8. So going back to the question, we are asked to find the number of terms in the geometric sequence. So 1/27 being the final term. And the number of terms is 8. N is equal to 8. So the number of terms in the sequence is 8. So this is just another way to solve the same equation. And this is the way the book does it, but I've added in a few extra steps as well because it does skip a few steps. So again, we have Tn equals A or to the power of n minus 1. Tn is 1/27. A is 81, or is a third. So now again, we're trying to solve for n to find the number of terms. So dividing both sides by 81. So we have 1/27 divided by 81/1. And that's equal to a third to the power of n minus 1 because the 81s will cancel on the right of the equal sign. Dividing fractions, the rule is we turn the second fraction upside down and then we multiply. So we're going to do top by top, bottom by bottom. So it's going to be 1 by 1 and 27 by 81. And that still just gives us a third to the power of n minus 1. So that can be rewritten as 1/27 times 81, again equal to a third to the power of n minus 1. So up here I've just put the term that has an n on the left-hand side, and I have the constant on the right-hand side, just because that's the way the book does it. So the 27 in the denominator can be rewritten as 3 to the power of 3, because 3 cubed is 27. And the 81 is rewritten as 3 to the power of 4. If you can't do that in your head, you can just use logs. So log base 3, 27 is equal to 3. So that's where we get the power 3 there. And log base 3, 81 is equal to 4. So that's where we get the 4 from. So ultimately we want them all to be have a base of 3. Because we have a third over here, we're going to end up having 3 as our base. So we want 3's on the right hand side as well. So that's why we decided to rewrite 27 and 81 as bases of 3. So a third to the power of n minus 1 can be rewritten as 1 to the power of n minus 1 divided by 3 to the power of n minus 1. Because when we have a fraction, we can apply the power to the numerator and to the denominator. And then the right-hand side is just the same. Then 1 to the power of n minus 1 just becomes 1. And the reason for this is, if n is positive, then 1 to the power of n minus 1 will always be equal to 1. And n has to be positive because n is a number of terms, it's an amount of terms. So some examples here, 1 to the power of 1 minus 1 gives us 1 to the power of 0, which is 1. 1 to the power of 2 minus 1 gives us 1 to the power of 1, which again is 1. 1 to the power of 3 minus 1 gives us 1 to the power of 2, which again is 1, and so on. So you could substitute any value for n, so long as it's positive, and you will always end up getting 1 as your answer. So that's why that just gets replaced with 1. Okay, so then we cross multiply. 1 multiplied by 3 cubed times 3 to the power 4 is just on the left-hand side. And that's equal to 1 multiplied by 3 to the power of n minus 1 on the right-hand side. So I've just taken this from the previous slide, which it's written down here as well. I'm just going to leave the rough work up for now. And when I need to, I'll rub it out when I need to write on the right-hand side. So I've gone from this step here over to this step. It's the same thing. I just wrote it out again. Okay, so 1 multiplied by anything is just itself. So I just have 3 to the power of 3 times 3 to the power of 4 on the left. And likewise, 1 times anything is itself. So 3 to the power of n minus 1 on the right. Then multiplying powers with the same base, we add the powers. So we get 3 plus 4 on the left. And 3 plus 4 gives us 7. Now we can cancel out the 3's because the bases match. And we have 7 is equal to n minus 1. So minus n is equal to minus 1 minus 7. So minus n is equal to minus 8. And n is equal to 8. So there are 8 terms in the geometric sequence. So we get the same answer as the previous method. So there are 8 terms in this geometric sequence. So another way of working this out, and you would have got full marks, is write out the first 3 terms and then write out some blank boxes with some commas in between, and then multiply by a third each time. So 9 times a third is 3, 3 times a third is 1, 1 times a third is a third times a third is a ninth, and 1/9 times 1/3 is 1 over 27. So alternatively, what you could have done each time is divided by 3. So 81 divided by 3 is 27, divided by 3 is 9, and so on. So we can see 1 over 27 is now our final term. We have a full stop to indicate that. And that is indeed term 8. So 1, 2, 3, 4, 5, 6, 7, 8. Obviously a much, much quicker method. And this method will not, well, not that it won't work, it will work if you have a bigger amount of terms. It will just take much, much longer. So if your final term ended up being, say, term 100, it would take a long time to write all of that out. So in that case, the algebraic method would probably be best. But for this particular example, it's definitely a lot quicker just to do it this way.